Hi, welcome back to the second week of the monsoon school. Hope you're rested up after the weekend and ready for another week's activity. So this morning we're beginning with Lenny Smith. Lenny was actually got his PhD in physics at Columbia. He's American, but he spent most of his career in the UK at Oxford, and now he's head of a center of time series analysis, or analysis of time series, CATS, at the London School of Economics. And he has a very fresh and provocative perspective, I think. Is that good? Lenny.
Thank you. Sorry we couldn't be here last week, but we were providing a provocative demonstration at the Royal Society on model output. Is there a remote control for the... Okay. So, thank you. So one of the things I want to talk about is model error. And this is an example of model error because it's supposed to work. Go back one. So on my way, yeah, the arrows.
And then the green thing with the laser.
Wait. Okay, so this is the entrance to the London Underground. And what you can't quite see, this is the entrance near the LSE. And you can tell that the elevator is closed. And what you can't quite tell here on the sides, on both sides, is each of these is saying that this is the next lift. Right? So both these two signs are telling me this is the elevator I want to take, and yet it's pretty clear this is not the elevator I want to take. Right? And very often when doing modeling, I mean not just weather modeling or climate modeling, but modeling almost anything, this is exactly what our models tend to tell us. And so the question I want to talk about today and tomorrow is, what do we do? What does data assimilation mean when the models are wrong, or when? So this actually was on the same trip. This was on the side of the train. It says, mind the gap between. And normally it says the train and the platform. It says the training and reality. Right? And that makes a huge difference when we're trying to do data assimilation, because, well, if we start, so what are we trying to do? I worked with Chris for a couple of years trying to figure out learn about data assimilation, and I'm still not sure exactly what we're trying to do. Right? So at first I thought the idea of data assimilation was to get the value at time 0. Right? So what's x? I mean, x is some state in a m-dimensional space. And then I said, no. So lots of Bayesians in North Carolina. There are a lot of Bayesians in North Carolina. So I said, no, the idea is to get the probability of x naught. So somehow I have to get a probability distribution. So I tend to work with very nonlinear systems. And it's very hard to get a probability distribution in nonlinear systems if m is about 10 to the 6. Right? So typical for a weather forecasting model. So then we come down, well actually, there are different kinds of Bayesians. Right? So even North Carolina even has some sort of theological Bayesians. Right? They aren't your normal Bayesians. They really think very carefully. And they say, well, what we really want is something like the probability of x naught conditioned on, and then there's always something interesting here, the information. And this, I think, is very close to the right answer. So what is this? Well, this would be the probability of x naught conditioned on what we know. So through the lecture, actually in about 3 slides, I'll try to start filling out, what is it we know? But then there's another question, right? So why are we doing this? Right? And this is a question I'll come back to also. So how many of you are interested in operational forecasting? Okay, and how many are interested in sort of making the model better? Model improvement? Okay, and does anybody not care at all about the model and just want to do better physics? Or understand the ocean, other than Emma? So this is Emma, laughing in the back. She'll give the tutorial tomorrow afternoon, and she'll also answer all the hard questions. So if you have any questions, especially in the next hour or so, please go ahead and ask, and then I'll ask Emma. So what are we doing? Are we trying to get x 0? Right? So I'm actually going to give half the talk at this board, and then I'll give the talk again over there, and then mix the two together, and hopefully it'll make a little more sense. So are we really trying to get x now? Or, so this would be now casting, right? Are we trying to get x for some future value of t? That would be forecasting, right? Are we trying to do some sort of probability distribution of x of t conditioned on something? So that would be ensemble forecasting. So how many people have worked with ensembles before? Have you heard much about ensembles? Some, not a lot. Okay, I'll talk more about ensembles tomorrow. Or you know, we may not really care a lot, or the reason that this model is being funded and ran may have very, very little to do with the value of some state variable in the future. It may well be a decision question, right? And decision, you know, the way we do data assimilation, it's really going to be different, right? I believe it's going to be different. If we're trying to do nowcasting, or if we're trying to do some sort of probabilistic forecasting, or if we're actually trying to answer a particular question, right? And that question might be a sort of weather-like question that you answer every day, should I carry an umbrella today? Or it might be a climate-like question that you really only answer once, like how high should I build this oil platform above the sea? Right? So there are these two very different uses, well, 3, 4, 5. There may be as many different uses of data assimilation as there are, right, different ways to use a forecast. And in some situations, they all have the same answer, right? You want to do data assimilation the same way. But none of those none of those situations are real. In the real world, where our models are wrong, where we have to deal with this question, right? In those cases, then data assimilation is an integral part of the entire process. And in fact, we may want to do data assimilation differently, depending on what we're trying to get out of the model. Okay, so I had a lot of trouble trying to figure out what the title for this talk should be, but I finally decided to go for geometry of data assimilation. I'll draw lots of pictures and circles and X's on the board, and if they don't make sense, it'll help a lot, everybody, except for Emma, if you just tell me. If you have a question, I'm really, really friendly. You know, just ask and I'll try to give an answer. So by the geometry of data assimilation, well, what do I really mean? Well, this is just trying to make the same distinction I made before. If you want to do mathematics, well, then you can just make assumptions and everything will work, and it's okay in those assumptions. If you want to do physics, you're a little bit constrained by the real world. If you want to do forecasting or you want to do decision support, then you get more and more constrained by the real world. And I think there's even some reasons for thinking that the question is, what are you trying to do decision support by someone who did a mathematical method of data assimilation? It's a lot harder, right? By trying to look at what the actual end-to-end process is, you get more information. So I'm Lenny Smith. This is a group at CATS, the Center for the Analysis of Time Series. And so most of the stuff I'm showing is coming from them. So, I think this is close to what I just said, but it'll be online so you can look at it later. We have to make this distinction between nowcasting, well, why, and forecasting. Why do we have to do that? Well, nowcasting, we value against the real world, right? We're trying to say, what is the state, say, of the atmosphere or the ocean right now? And we compare that against observations. Now, those observations may be from a thermometer, or they may be from an oil rig that falls down, right, because of excessive wave heights. But the question we're looking for is what's going on right now, and the verification is ideally a measurement of that thing right now. This is really different from forecasting, where we're now going to take an initial condition, or an ensemble, a set of initial conditions, and put them into our model and move them into the future. So data assimilation for nowcasting, well, that just depends on data assimilation. Right? If you do the data assimilation well, you get the measurement for what's happening somewhere you didn't look well. Forecasting, that's a blend of data assimilation and the actual model. So if the model isn't perfect, and the data assimilation is perfect, I'm not sure what it means, actually, right? But let's say data assimilation is perfect for nowcasting. We then put that in a model and move it forward. And what comes out is nonsense. Well, you can't fix that by improving the data assimilation scheme. So the goals are different in these two. We also have to keep a clear distinction between the model and the system. Right? So, well, if we're doing maths, we don't. They're the same thing. But if we're doing physics or forecasting, then those two things are different. Right? Yeah?
You said you can't fix that by improving the data assimilation.
Sorry?
So you said you can't fix that by improving data assimilation.
Right.
But I guess you can try to fix that by trying to fix data assimilation by taking into account the body.
So that's right. So the question is, can you fix, so you run your data assimilation scheme, something comes out, it goes horribly wrong, somebody comes back and yells at you, and you say, no, it's the model, and then somebody goes and yells at the modelers, and they say, no, it's the data assimilation people, then Emmett would say, well, it's me, it's my model, but really, it's the data assimilation's people's fault because they should have taken care of the fact my model wasn't perfect, right? So that's possible, and in fact, I think there are things we definitely want to consider that change data assimilation given the properties of the model. But I think probably it works better to go the other way, and before the model goes wrong, before the forecast goes wrong, right, write a note to the modelers telling them from the data assimilation, tell them what's wrong with the model. And then if they complain, you can say, but we already told you this was what was wrong with the model. But it's true, the two have to work together. The entire process has to work together. So I'd also argue that we can provide better information using models and data assimilation, but again, I wasn't here last week, but I know the people who were. And you know, this idea, this word, well, I don't think we can provide probability distribution functions. I don't think we can provide probability forecasts. Right? Well, we can, but I don't think we provide probability forecasts that you'd be advised to use as probability forecasts. Okay? So I'll come back to that in just a minute. So if we let go of this, then, and I think only then, we can actually accept the fact that the observations are noisy, the linear regime, the time over which I can treat my model perturbations as being linear, that's really short, and the model is obviously inadequate. And we can still make better decisions based on the stuff we put in, right? So this is what I was starting to write before. This is where I really want to start. What's the probability of the initial condition conditioned on the information? Right? So what is the information? Well, oops. So what do I have? Right? Well, I've got my model, but in fact I actually have something bigger than my model. I have some class of models, some set of functional forms. And maybe, in fact, in an operational case, it's something that actually fits on a computer that runs faster than real time. Okay. In these models, I'll have some parameters: the freezing point of water, the lapse rate, some parameters that I actually have to put into the model at some point. I may not know the values of those models. I'll also have some observations. Okay, and finally, I've got some computational limits. So I'm really not going to talk about this very much, but this is, of course, critical, because if my model runs slower than real time, it's not very useful for forecasting. It's still very useful for physics, and maybe it's completely irrelevant if you're doing mathematics, right? But for forecasting, these constraints are really very severe. So what do I mean by a model class? So I'm going to assume that my model consists of just one model for the moment, right? So I have some model f of x. And what's going to happen? Well, I have this value x, which is sitting in my high-dimensional space, and I'm going to move it forward in time to some new value, okay? And I'll leave things discrete because it's easier, and once I put it on a computer, it's going to be discrete anyway, but it all goes over to the continuous time case. So I have a question. Let me assume for a minute that there is, in fact, a model that generated the data, a perfect model. If you don't want to believe in a perfect model, you don't have to. But I have a question, right? Is my perfect model contained in the set of my possible models? So there are only two options. If my perfect model is in this set of models that I have, then everything works and life is easy, and I'm a Bayesian, right? But if I don't have a perfect model, argue if a perfect model doesn't exist, I don't need anything that philosophical. All I need is that the model that generated the data isn't in the available model class, then everything changes. Right? And in operational forecasting, this is the case we're always in, except for when taking exams, and maybe in the tutorials tomorrow. Okay? So that makes sense? In one case, I actually know what generated the data. Right? My model generated the data. And then I can make many, many more, well, I don't need to make assumptions anymore. If my model didn't generate the data, then the basis of data assimilation becomes a little more questionable because, well, now there are two different things. There's the model state and the model. And they have some strange relationship to the true state, if such a thing exists, and the true, excuse me, and the true model. Okay? So that's the model state. What are the parameters? Well, I'm just going to assume my parameters alpha are in some L-dimensional space, but I'm going to have this same sort of question. In a perfect model, there are values. They are uncertain, but they exist. But if my model isn't perfect, then what's the right value to use for a parameter? Yes?
I just have a question on your sort of framework for modeling. So I guess where I think about it is the model, the goodness of a model depends on what the objective using that model is. And so when you say perfect, you mean perfect to the physics?
So I mean structurally, I mean mathematically, structurally perfect. So in that case, in the case of a perfect model, the same model and the same parameter values are optimal for all questions. Okay. So it's a good question. Let's say my model is something like, so how many people know a little bit about chaos? Chaos? So if I say logistic map, a few, okay? So this is the logistic map, right? So f of x is lambda x times 1 minus x. So it's sort of a very common, simple model that happens to be chaotic for some values of lambda. So that's my model. Let's suppose and I'm going to drop the tildes on the x for my own sanity, okay? But remember, this is the real world. It isn't quite like that, right? I have a constant plus a constant times x plus a constant c1 plus c2 times x squared plus c3 times x cubed plus c4 times x to the fourth, where c3 and c4 are much less than 1. Okay? So by structural model error, I mean we assume, so I could rewrite this and work out what c1 and c0 and c2 really were, right? Structural model error means I assume the model is quadratic, but the real world is quartic. So I set c3 and c4 to 0. Well, actually, I don't even know they're there. This could be the hyperbolic tangent of x over 10 million, right? It could be any small term. So when the system is linear, then I just lose a little variance. Nothing horrible happens. But when the system is nonlinear, because of this because of all of these terms, right, then horrible things happen. Okay? So does that make sense? So my model imperfection is having the wrong functional form for f. So I could think Navier-Stokes are perfect for fluids on a sphere, but I only have a truncation of Navier-Stokes on a digital computer. That's enough. Or I could think something larger, like my model doesn't actually resolve the Himalayas very well. Or the Andes are completely missing because they're too narrow. Right? There could be really big things, or there could be relatively small things. Once this happens, then, in my view, data assimilation changes completely. Okay? So, and a simple way to see that with the alpha is just to say, well, if these really weren't there, right, then in this case, alpha is just the vector c0, c1, c2. And what I'd want it to be is, well, this is just lambda x minus lambda x squared, so I'd want 0 lambda squared. But if the system was generated by this model, which has these two values, then would I want to put this value for lambda, would I want to put this value, or would I want to put something that works? And there I would take your position, right? If I had a particular problem, which will be different for nowcasting, forecasting, ensemble forecasting, and decision making, I would want to use the values here that worked, not their true values. So it doesn't bother me very much if the acceleration of gravity in my general circulation model isn't about 10. It doesn't bother me at all. I mean, if my resolution was very, very high, it doesn't bother me if water doesn't freeze at 0 degrees. Right. If in fact it gives me a better model. If my model had a resolution of angstroms, then I would want water freezing at 0 degrees to come out with the model automatically. Okay. But again, what you're going to do depends a lot. Where you're going to go depends a lot on what the actual aim of the model is. All right? Okay, so that's parameters. Next we have, so these little funny signs. That's, these aren't really mathematical. These are information objects. So that's why I have the little funny caps on them. What is S? S is the observations. Okay? And typically I'll say something like S is equal to some set S sub I, X sub I plus epsilon I, where epsilon I is normal 0 sigma squared, something, so this is a standard sort of noise. Here, well, I got a problem already, right? Because really this is X twiddle, but that's okay. So I make an observation. These are numbers, right? So here I really am a Bayesian. The only thing I really have are those observations. And then I try to say what those observations come from. So those observations come from the true value of X, assuming such a thing exists, plus some noise, right? And then there'll be a set of these where I denotes time. Now, of course, in reality, the noise may not be like this. The noise model, now I have another model. This model can be wrong too, right? And almost certainly for physical measurements, there's hysteresis, things aren't IID. And last is the computing power. And so I'll just assume, for a little while, I'll assume this is infinite and not worry about it too much. So, again, this is what we were just saying. These are the difference. I want to be able to estimate what the current state is of the atmosphere of the ocean, or I want to estimate the future state, or I can try to get probability density functions for these two, or I can actually worry about forecasting forward in time. So why is this different? Well, it comes back to this question again. Suppose I'm making a forecast a day in advance. Well, if my model is perfect, the way I do data simulation for a one-day forecast is the same as the way I do a data simulation for a two-day forecast, or a 3 or a 4 or a 5-day forecast. But if my model isn't perfect, then in fact I can worry about ensemble formation, forming initial probabilities. Those needn't be the same things as I move further and further into the future. In fact, once my model isn't perfect, even the parameter values are questionable. Now, I'm not suggesting in operational systems that we start adjusting parameter values for the target, but just that when we interpret the outputs, we realize this is true. So, do we have to assume when we're doing data simulation that the observations are noise-free? Well, no. Almost nobody does that. Do we have to assume that the observational noise is small? As in the time over those perturbations grow, we can treat things as linear? Well, yes. If things become horribly nonlinear, the common filter is gone. Right? It's not optimal. It's not even suboptimal. It's sort of silly. And if you go back and you look at Kalman's paper in 1964, or whenever it was, the very first footnote says, what we really want to do is have a nonlinear process that does this, but we don't know how yet, so we'll stick with this linear process. So again, the idea of taking this the linear methods and applying them to nonlinear models, what we need to do is just go ahead and check, right, afterwards. Are we doing things that actually make sense? So how would we know? Well, in our model, I'll often draw a noise ball around the point. And just like I take x forward in time, I can actually take this noise ball forward in time. And if things are linear, I'll get an ellipse. Okay. And then I make a new observation. And I can follow the common filter here, and everything's fine. The common filter work. This is where x goes forward. In fact, our observation wasn't at x, and so it goes somewhere else. Well, if we make another observation, it just falls somewhere else. And the common filter is effectively a way of combining this spherical information from the observation of truth with this ellipsoidal information from propagating forward the uncertainty around our initial observation. Of course, if the time scale here is so long that this thing is a horrible, nasty swirl, then that's a silly thing to do. And if the model error is too big, then this actually ends up over here somewhere, right? We don't even have consistency between our forecast and the next observation. And this is when you start inflating things like variance inflation, or it's interesting if you look at the reported uncertainties and observations and the actual covariance matrices used in practice. Very often the modelers, the theorists, take observational uncertainties which are much larger than what the experimentalists assigned to the measurements. So perhaps they can say this is representation error, or perhaps it's just that the model is wrong. Right? I don't think we can really sort those things out easily. Do we have to assume that the model variables are state variables? Well, this is a question of representation error. We're observing at points and we're trying to estimate a field, so it's very reasonable to say we have a map between these spaces, right? But that's really hard, and I'm effectively just going to write x all the time. But we shouldn't forget that problem. We have to assume that the model is perfect. Well, variational assimilation assumes that the model is perfect. So the whole idea of variational assimilation so this should be clear. This is t equals 0, t equals 1, t equals 2. Variational assimilation accepts that. How did I lose the blue one? When we take this point forward, we get something that's sort of like an ellipse. We better include there, right? Something that's sort of like an ellipse. But if we take this point forward, we get an ellipse here, and we begin to get something really rather different. As time goes forward. So anything that was initially inside this circle gets mapped to something inside this ellipse, gets mapped to something inside this shape. Okay. So what variational assimilation tries to do is it picks a point in here and moves it forward, and then moves it forward again, and like before, I need to make sure reality is in here too. So if I start with a really good guess, let's not start with that guess. Let's start with a really good guess. That moves forward, that moves forward. Variational assimilation just tries to move the green dots down to the black dot, right? So we just have a cost function which says minimize these distances by varying the initial condition, and it just walks straight down and converges. But what happens if we happen to start slightly off? Well then, our point's slightly off. We're off here. Variational assimilation runs down and hits this wall. So variational assimilation can get trapped in local minima. What happened to the common filter? Well, the common filter, well, it's assuming that this is an ellipse. Well, not quite, because it's only going one step at a time. So in fact, the common filter might be okay here. You might approximate the blue thing as an ellipse. But you've given up the memory of earlier times. So that's the balance between these two approaches. One approach, the filter, you're only looking one step ahead. So you're assuming everything can be encapsulated at one time. But you've lost memory of the earlier points. The variational method, you have this memory over a window, but in normal variational methods, you have this horrible problem of local minima. You can't actually, if you have a good initial choice, you're doing fine. If you have a bad initial choice, you literally get stuck. And that's assuming the model's perfect. If the model's not perfect, I don't understand why you would even take a variational approach. You don't expect the one that minimizes the difference to help you. And we have to assume infinite computational power. So I may talk about this a little bit at the end of the second lecture, but for now I am. Right? So none of this is going to get better for finite computational power. Oh, and yeah, I haven't been here last week. I don't know if anyone has said optimal so far, but this idea of optimal, if you're doing maths, maybe even if you're doing physics, you can say optimal. But once you're doing operational forecasting, I think you should say better. Because once we're in this situation, then we can be optimal here, but we really know we're not optimal here. Okay, so this is just to say that the same question again. I'm not against optimal, right? It's just a question of what you want to do. So Borel, who invented the idea of having a semi-infinite number of monkeys typing randomly in 1913 or something and giving you the works of Shakespeare. So this is a maths problem. You can work out this problem, right? And we can think about linearity or perfect models. I haven't said anything about whether the models are stochastic or deterministic, but that goes there too. Probability theory. These things sit down in here, right? But once we get over into forecasting and decision support, this is a real crop circle. Right? It wasn't formed by aliens. It was formed by people in Britain protesting genetically modified food. But once you get over here, we just have to embrace these questions about what we know and what we don't know, and even for climate change, ethics. Right? They're just more interesting questions. Okay. So in the notes, I'm going to just walk through these. I'm actually not even going to walk through these. Well, I'll talk about this slide and then I'll skip the rest. So I'm really happy to talk about any of this stuff. And what we've done, I've got references that should have hot links when these are on the web, so you can see the papers we've written. We're really interested in these questions of model improvement, and you will see more today about imperfection errors and pseudo-orbits. About model evaluation. So once you accept that things are nonlinear, root mean square evaluation really can lead you astray. So I'll show you a simple example in just a few minutes. How do you evaluate forecasts? And actually, this is interesting in two ways. How do you measure the skill of forecasts, but also how do you communicate forecast information? Okay. How do you improve the model? How do you do nonlinear assimilation? Can you actually spot? I'll just stop at this one in a minute, because this is really good for the common filter and for ensemble formation and for variational assimilation. How long can you actually look at the linear assumption, and how do you make decisions? So, again, if you look at these online, you can just click on that. Hopefully it will give you the relevant paper. And then a little more on what happens when things go nonlinear. So this is a probability forecast for the Lorentz equations, the famous 1963 butterfly equations. And this is time going up, and this is the value of x going across. So then this is just the probability of this value of x. And you remember, x is the speed, the wind speed going this way, and y is the wind speed going this way, and z has something to do with the temperature gradient across the cell. So what you see is the probability density starts moving out and it spreads out. That looks sort of normal. And then it gets tighter again. So it's easier to forecast this system out here at point 2. The PDF is peaked than it is at point 1. So for a linear system, that cannot happen. Right? And there are huge arguments in atmospheric science. I don't know about oceanography, whether or not you actually see this in the real atmosphere or not. And then it comes down. This is again the PDF moving. There's a little bit of probability running over there already. Comes up, comes down, bifurcates, that it changes color. So the reason it changes color is the color is the standard deviation of the ensemble. Okay. And when it goes blue, if you're using root mean square forecast evaluation, it tells you there's no information at all left. So basically about at this point in time is when evaluating your forecast by looking at the RMS error says there's no information in the forecast. But it's clear there's a huge amount of information in the forecast, right? There's still a lot of information in this probability distribution. When you get about here, things are even worse. So this is roughly a symmetric probability distribution. This just corresponds to, there's a 50% chance of being out on this wing and a 50% chance of being on this wing for those two big wings on the attractor. So a 50% chance of strong winds from the east and a 50% chance of strong winds from the west. So what is the optimal root mean square forecast? Zero wind. Okay. So these little mathematical questions have huge impacts if you're trying to make decisions about whether to go sailing, right, or go outside even, right? So on the other hand, if you evaluate this probability distribution as a probability distribution, it is perfect. In this case, I have a perfect model and I have a perfect ensemble. And I need both of those. That initial ensemble is the data assimilation part. Right? How I form this initial ensemble when my model is perfect will depend on how far into the future my ensemble looks good. So even with a perfect determinist O, then of course, there's a lot of talk about chaos, right? And chaos limiting forecasts. if you actually read some of the papers Ed Lorenz wrote in the late 60s, he points out that there are limitations to the limits on chaos. They don't necessarily limit things like seasonal forecasts or climate forecasts, because these things, the Lyapunov exponents, are sort of the things that define chaos. They describe the exponential growth. I think that phrase was used last week. But they only apply to infinitesimal perturbations, infinitesimal errors. As long as the errors are infinitesimally small, they're not going to cause a problem. And as soon as they become finite, then these Lyapunov exponents don't apply. So, you know, here we're looking, the Lyapunov time is somewhere in here, but we're looking well beyond the Lyapunov time, and still there are big clumps of probability mass moving together. Chaos needn't stop even weather forecasting, right, depending on how good your data assimilation is. So what does? Well, what I tend to look at, and I'll show you how in just a minute, is the limits of predictability are basically when the probability that we forecast is worse than climatology. Okay? So as we're going into the future, eventually, if our model isn't perfect, if our ensemble isn't perfect, if our computer isn't perfect, unless the computer generated the reality, then our probability distribution will be worse than just making the climatological distribution. So an interesting question is, there are two questions. How do we get that probability from an ensemble? And then the second question is, when does that happen? How do we measure the difference when we have two different PDFs? Okay. The root mean square forecast is at best irrelevant. In fact, it's pretty misleading. And how do we measure these scores? Okay. So I want to evaluate my data assimilation scheme. But hopefully now you believe that I really don't want to just have a point here. What I want to have, well, what I'd like to have is a probability distribution, but I don't know how to do that in 10 to the 6 dimensions. So what I end up with is a sample, some initial ensemble of points. And then I take this ensemble and I move it forward, and I try to work out a probability forecast, or a probabilistic forecast. With some offset and some width. I could make it more complicated, but it doesn't help a lot. Right? And on each of these individual points, I'm going to add this kernel. So basically I'm going to take this kernel and put it on every point. Then I'm just going to add them all up. So P1 from my ensemble is just the sum of kernels, these kernels, based on every observation I have, right, divided by the number of observations. And then when I go into forecast mode, and maybe even in data assimilation mode, right, if things aren't going well, I also know the climatological distribution. So this is my prior. This is my unconditioned distribution. This is the distribution of all temperatures on July the 11th that I'm looking for. These are my data. These are my estimates of the current one for my data assimilation technique. I'm going to turn this into a climatological distribution in the same way. And then I'm going to just wait. I'm going to mix these two together. I'm going to blend these two together. Yes? Sorry, how is that?
How are you placing the kernels on the various points,
So I do some data assimilation scheme, right? So this could be points from my particle filter, or points from my ensemble common filter, or parts from my variational method. Well, variational method only gives me one. So, but I have a variety of points. And if you think about it in the forecast thing, then these are the images of my ensemble forecast. Okay? So these are the inputs that my model gives me. And in a few minutes, I'll compare an ensemble common filter and the method that we use. And I already have these points, but I need to show you this first in order to show you how I compare, why ours is better. Okay? But it would show ours is better almost any reasonable way. That's the definition of a reasonable way. So, okay, so now I have these two distributions. What am I going to do? I'm going to take these two distributions and add them together. So my forecast distribution is just going to be alpha times my probability forecast plus 1 minus alpha times my climatology. So I hope right? If my data assimilation scheme is good, or if my forecast is good, alpha is about 1, and most of the weight goes onto the assimilation scheme. In fact, because I only have a finite ensemble, there's a chance, and things are nonlinear, there's a chance that things are far away, or I just had a very bad observation, or a large observational noise increment. Then in fact I'll put more weight on the climatology. And when I am making forecasts, right, I can actually watch how alpha changes as I move further and further in time, right? So now I move into this question of looking at things going forward. And once alpha becomes close to 0, right, there's no operational reason to keep running the forecast. Although this tends to happen significantly sooner than the end of the forecast time at European and American weather forecasting centers. Okay? So what does this have to do with data assimilation? Well, your choice of data assimilation algorithm is going to depend on the aims, as well as the quality of the model and the accuracy of the observations. Right? And again, outside the perfect model scenario, we don't have an optimal, but they're better and worse. So I want to show you one more example of why I'm going to, and then I'm going to step back and only do nowcasting. So I don't just look at weather, because it takes too long. Certainly climate takes longer. We look at quite a large number of different kinds of dynamical systems. And this is maybe the simplest one. This is it, right? This is a circuit where we actually are measuring 5 outputs at the same time. But you can treat it just like the atmosphere. So let's say we do data assimilation over this period of time at the beginning, up to time equals 0. And then we launch an ensemble of 512 points. That's these light color. Can you see the blue? Yeah. And this is what actually happened. So we only take data from before time 0. We have a very sophisticated data assimilation scheme that isn't perfect, but it's pretty good. And we launch the ensemble. And the thing you should notice is the entire ensemble goes horribly wrong about here. The real world turns around and goes down. And all 512 members, and in fact, a very much larger more members, right, don't make this cut. So the point is, if I'm evaluating my data assimilation scheme on forecasts, I want to make sure that I don't blame the data assimilation scheme for things like this. There is no initial condition that we can find, and I believe there is no initial condition consistent with this piece of trajectory that actually makes this cut. This is due to model error. Okay. So we can look at a different model. And in a different model, we actually manage to get a place where some of them go up and some of them make the cut. So again, fixing this kind of problem I think is hard to do by fixing this problem is impossible by improving the data assimilation scheme. Because for this point, there is no set of initial conditions that actually shadow, that stay close to this dark line all the way to here. For this model, there might be some way of improving things, because at least it does shadow. Okay? But I think it's better to try and keep these two things apart if possible. Okay, so, and that wasn't a special case. We look at many times what we see, this is the same sort of thing. The entire ensemble ends up moving off at the same time. Now sometimes the ensemble spreads out a lot and we end up getting something like climatology first, but this happens a quarter of the time. Okay? So again, we don't want to blame our data assimilation algorithm for model error. So how can we do that? Well, we do that by just trying to analyze what's happening at t equals 0. We're going to do the same sort of kernel dressing, right? But we're going to do it back at time equals 0, just to do nowcasting. Okay? And then we also have to make this choice, because our model isn't perfect. We have to make the choice of what counts as good and what counts as useful. So the models are useful. Well, the question of what score, we'll get to this in a minute. What scores are good? So we're actually going to look at a log p score. I know this is a lot of stuff at the same time, but ask me questions later in the week. We're going to look at log p scores. We're going to try and score that ensemble. We'd also say the data assimilation scheme, things are good if we actually if we just understand things when we put them through our model, so we make better decisions. Maybe if we can't get here, we just get down to questions about we understand the system better. So, we can back way off, even though our models are wrong. And how can our models be wrong? Well, our models can be wrong mathematically. They can be empirically adequate, right? That means they're close to perfect, but they're just wrong on some technical reason. So I don't have any physical systems, not even this one, right? I mean, I've actually spent 10 years looking for a system where chaos was the problem, and I can't find one. It's always model error. A real system, not a mathematical system. So we can be wrong and says that the shadowing time is long but finite. Well, what's the shadowing time? Well, the shadowing time is just to ask, if I tried every single initial condition in here, if I tried every point inside the 0.999 probability isopleth, and I moved all those points forward in time, how far would I go before all those points were outside some acceptable region? And it turns out, so if the model is perfect, in this case, it's forever, right? In this case, the trajectory that generated the data is in there somewhere, and I may not be able to find it, but that's the problem of data assimilation. In this case, if the model is chaotic, it's not forever. There's some finite time, which may be 2 days, or 10 days, or 2 weeks, at which more than half the time that there is no initial condition which will shadow. That's not a problem of data assimilation. That's a problem of model error. And it can even be the case that the two are qualitatively dissimilar. So you know, if you look at climate models have systematic errors that are large compared to the change in temperature in the last century. That doesn't mean they're useless, right? They can be very useful for scientific understanding. We can have models which really don't look like the system a lot, and they can still teach us a lot about the system, but we probably don't want to try to be making probability density functions on them or basing qualitative decisions on them. Okay, I'll come back and do that tomorrow. And so you've had the Ensemble common filter. Have you had lectures on the Ensemble common filter yet? Yes? Okay, there's one more point I want to motivate, and that's, you notice I sort of drew all my green dots on a line here. Well, that's because almost all of our models are dissipative in the sense that not all the states in a sphere, if we look at a sphere in our model space, right? So if we look at a sphere of a weather model around a point, lots of those states are effectively not allowed. They're not necessarily impossible, but they're out of balance. They don't obey some hydrostatic restrictions. As we move our model forward, in that space, the models tend to collapse on something like a manifold. Right? Maybe it's an attractor, maybe it's not, but we don't see action in the entire 10 to the 6th dimensional space, or data assimilation would be impossible, right? So we're sort of lucky. So a manifold is something like a street, right? It's something that we're trying to, it's something that the model is evolving along. And we have an observation with a covariance matrix. The observation is almost never on that manifold. With probability 1, it won't be on the manifold. Okay. So how does the common filter work? Okay, so I think I've done everything here. So we have an observation. We actually know our observational covariance matrix. We have some manifold, but we don't know where it is. Well, how can that be? Well, usually we have non-constructive proofs that the manifold exists. By looking at the equations, we can prove there's a manifold, but we can't actually find it without running the model forever. Okay. So we know this exists, and we know this isn't on it. So what do? Well, this is the bus that goes from downtown Boulder up to NCAR. And I would argue that it has about 11 degrees of freedom, you know, where the wheels are, where the bus is, and some of them don't matter, which windows are open. So I ignore those degrees of freedom, and I just keep the 11 degrees of freedom that matter. And you know, NCAR is a very hilly place, so actually this bus explores a lot of these options. And so I can work out a covariance matrix for the location of the bus. So I want to make an ensemble. Now, this isn't the way I suggest we make ensembles, and I'll tell you something different tomorrow. But here's my initial condition. I sample my covariance matrix, and so I get different buses. And they're in different places. Some of them are embedded in the ground. Some of them are not in a very healthy position, right? But these are just samples from my covariance matrix. And I can't tell, because I don't know if I happen to be on the hill going to NCAR, whether this is a good sample or not. Now I take this ensemble and I move it forward. Let's say my model is perfect. I move these guys forward, and this is what they do, right? These guys look pretty good. So, what should I do? Well, what does the ensemble common filter do? I get a new observation. It more or less looks at these guys, at this observation, and resamples the covariance matrix that gave me this. All right? So do I want to have, again, all these possible orientations, or do I want to try and somehow take the fact that I know these particular trajectories, right, are on the manifold? Can I use the geometry of looking at long trajectories, the way variational assimilation does, not to just resample from my error covariance matrix? And so I would argue that I don't really want to make an ensemble filter update at this point. Okay? This is really what I want to do. So these are results with Sri Care, and there'll be other results by Du. This paper, I think, just appeared in Monthly Weather Review. And this is where I thought I was going to be getting to the end. I'm a little ahead. But I'm trying to do data assimilation here. These are all nowcast pictures. So we're looking at a two-dimensional map. This map really does have an attractor, and these little dots are showing you where the attractor is. Okay. The cross is showing you where truth is. So right in the center here is the value that generated the observations. In fact, it's along a trajectory, a long trajectory that we have observations on. And then these are just 4 different realizations. Oh, and this is the observation. So what are these colored dots? This is the ensemble common filter that Sri used in his thesis at NCAR with Jeff Anderson. Right? So this is the way we sort of try to work in CATS. If I was to build an ensemble common filter, it probably wouldn't work very well. So we got Sri to build an ensemble common filter, and then we got Sri to do the gradient descent method, the method I'll explain in just a minute, and we compare these two methods. So if my method beats my common filter, I'm not very happy. But if Sri changes and decides that his thesis is the thing he built in his thesis works worse, then I am happy. Well, at least I learned something. Right? So and what do you see? Well, this is the sort of thing you see. These dots, they're colored by their probabilities, aren't equally likely. The common filter ensemble is equally likely. This is the observation. This is the sort of typical thing you see. The observation happens to be far from the truth, and the entire common filter, the entire ensemble, the pinkish ensemble gets pulled towards the observation too much. Okay. Of course, you notice that this ensemble tends to fall close to the crosshairs, so that's good. We're actually putting probability density close to truth. But the other thing to notice is that it also tends to fall on the manifold. So again, if you think of this attractor as the sort of set where reality, the true state is going to live, so we're definitely in this case, right? Then we find that even when the system is wrong, so here, what happens in this case? What you can see is that while the common filter moved the ensemble towards the observation, the gradient descent approach, or ISIS, actually tends to move the probability mass towards the observation, so the high probability points move down, but it still stays on the relevant part of the attractor. In fact, it still comes rather close to the target state. Right? So the idea is not to try and ignore the fact that we also have a long series of observations in the past, which are completely inconsistent with the filter result, right? But to use that long window as well to constrain to constrain the location of the points on the attractor, and then allow the probability density to shift. If in fact this is an unlikely event, it can shift back in the next step. Because there's no way for us to tell, right? There's no way to know at this point from only observations if this is an unlikely observation, right? And in fact the truth is down here, or if the previous observations were better and truth should be up there further. So how do we judge these two methods? Well, consider if we put a series of balls around the crosshairs, and we just count the probability mass that each method puts inside, right? So again, here's the common filter, ensemble common filter. Here's the observation. The crosshairs are truth. We can look as a function of epsilon, which of these two different methods puts more probability mass close to the target. And yeah.
The observation and noise is fairly large in the sense that the previous picture.
So in the
In the previous picture, the one, yeah, this one. To both the ensemble Kalman filter and ISIS ensembles lie within, say, 95% of the observation of.
That's right. So in this case,
error.
they both lie. Well, I could actually show you that on the next slide. So these were chosen. Actually, these were chosen in order to get particularly large realizations of the noise, so that you can see that. So that you can see this effect, right? But I think in the next slide I can show you exactly where they lie relative. Oops. Exactly where they lie relative to the noise. Yeah, I mean, I should have a statement of the noise in just a second. So I think the noise. I don't have an axis. I think the noise. I think the noise will be in the next caption. Okay. So what I'm doing is I'm drawing different sizes of circles and asking how much probability mass fall inside. So one thing I could do is I could just take the observation and I could look at the inverse noise because it's Gaussian. So I could draw a very, very cheap ensemble just by putting the inverse noise on the observation, and I could ask how much probability mass that puts inside. Does that address your question? So if the observational noise was very small, then that would work really well. If the observational noise is very large, then you won't get much probability density inside the sphere. But I hope this says yes. So here the noise level is 0.05. Right, or yeah. Now what's this is showing is how many times does this gradient descent method actually put more probability mass than the ensemble common filter. That's the red line. So on every case, every assimilation, we have a contest. Who puts more probability mass close to truth? And if they tie, they both get a point. Right? That makes the ensemble common filter look better. Okay. But what you see is, especially for small distances, and in fact at almost all distances, right? Except for very small distances, nobody puts any mass, nobody gets anything there, so they tie, right? But on a large range of scales, the gradient descent method actually puts more probability mass close to truth than the filter. It puts much more than weakly constrained 4D var and much more than the inverse of the noise. So the noise level is around 0.05. So at the noise level, for a ball the size of the noise level, we're still putting a lot more mass inside. Does that answer your question? Yeah. Okay. So there's a technical problem, which I'll finish after I explain. This epsilon score is not proper. You can actually find ways of gaming it. Proper is a technical quality of probability forecasts, right? So yeah, if your score isn't proper, then what it means is that there's a probability density which isn't the right one, which will get a better score. Right? So you would like your scores to be proper. So we also evaluate it using, we evaluate these two data assimilation methods using this log p score. This score is proper. You can use other proper scores too, but don't worry, I mean, you don't really need to worry about them. The main thing I want to show you here, these are just some more examples, these by Do. Here's an example again from a high dimensional system projected down. But this is really what I want to show. In this case too, the ensemble common filter does relatively well. The gradient descent does better. So this score is oriented negatively, so smaller values, larger negative values are better. And it reflects the number of bits, right? How much more information is provided in the probability distribution. So a difference between 4.5 and 3 for this two-dimensional system would be, that's a difference of 1.5 bits. So 1 bit is a factor of 2. 1.5 bits is 2 root 2. So that's 2 times 1.5. So it's about 3. So in this case, the gradient descent method puts about 3 times more probability mass on truth than the ensemble common filter. Okay. And that's a lot. Right? Moving up to the 12-dimensional or 16-dimensional system, whatever it was, we see that it's not quite so big, but now we're starting to work in much higher dimensions, and we're still getting a difference of, almost a bit, more than half a bit. So more than 40% more probability mass on the truth. And you can also see that, remember, how are we turning these things into PDFs? So we're putting little kernels on them. So if things are doing better, you would expect the kernels also to be smaller. And if you actually look at the kernel widths, they are smaller, right? So for gradient, in the two-dimensional case, this is 0.02, this is 0.001, 0.3, 0.07. So the point here is that the ensembles that are coming out are closer to the target, and they have so they can have much smaller kernels on them. They give you a much denser probability distribution, as well as giving you more probability mass on the verification. So if I have time, I'd just like to show you how this works, and next time we can talk about the math.
So doing
yeah.
two terms, gradient descent and ISIS.
So gradient descent and ISIS are slight variations. I didn't have time to make my slides uniform. So gradient descent and ISIS are the same thing, are effectively the same thing. Okay. The key difference is one has to do with how you get this initial, how you form the ensemble. They're identical in the thing I'm going to show you today. And I'm going to tell you right now what the gradient descent is, and then I'll tell you tomorrow the whole thing. Okay. Okay. So this is again the Lorentz attractor. So this is sort of that two-dimensional. This is one of those wings going around the side. And here is truth. So I'm in the perfect model scenario. Truth at time equals 0, 1, 2, 3, 4. I'm going to make observations. So I've got 4 observations. And of course, they're not on that leaf. These guys are on the leaf. But these are somewhere in that whole three-dimensional space. In fact, all I have are the observations. I don't really know where truth is. So I have my model. And from my model, I can actually make a forecast one step ahead. 1 step ahead, 1 step ahead, and so on. And now this is yet another term. This is Kevin's term of the shadowing filter. This is this gradient descent step. What I'm going to do, and I'll go through this really slowly tomorrow, so don't think, just watch. Right? There's a difference between the image of the first point and the beginning point of the second point. Right? There's a difference between the image of this point and the next point. So these little pink lines are my mismatches. It's the mismatch between the forecast from the initial condition and the next initial condition. Okay. So what I want to do is simultaneously shrink all 4 of these points.
All the initial conditions are observations.
Sorry?
You are starting with observations.
Correct. I'm starting. So I need an initial point, and that point is a pseudo-orbit. In this case, it's the observations. In the case of an operational model, I'd have to start with something like a very cheap analysis. Okay, and I'm actually I'm doing this simultaneously in a higher dimensional space. I'm just doing gradient descent to shrink the sum of these points. And what happens is I move towards a trajectory. Right. So I don't actually get a trajectory unless I run this forever, but I can always take one of these points and run it forward if my model's deterministic and get a trajectory. And then what's the properties of that trajectory? Well, it turns out it doesn't have to be near truth, but it is near truth. It's almost always near truth, right? And if I turn the attractor around, I see, so what I've just taken the sheet and moved it so you can see it sideways. Right? So here we're looking at it from above, sliding down so you see it from the side. The trajectory is also quite close to the manifold, close compared to where the observations were. And well, let's see, what would happen if, instead of having this point, I'd had a very strange observation here? Well, a filter, a one-step filter, sequential filter, once it gets pulled off by this, it's going to be off for a while. Particle filter as well, right? But the idea of the shadowing filter, the same way with the variation, any method that looks at a long window, is it's trying to minimize this leg and this leg, as well as these two. And it can minimize both of these by bringing this point in. And so that's exactly what it does.
Minimize with respect to what?
With respect to these, it's trying to minimize the sum of these distances.
With respect to what?
Well, Well, these points, the initial points here define the images, right?
So what's the free variable?
So it's actually this variable. I think it's about 2 slides. So what I have is I have a vector which is actually in a space, which is the dimension of the space times the number of observations. Okay. This vector starts out at time 0 as just the observations. Okay, so this is actually the sum of all these points. So the free variable are actually the coordinates of all these points on the pseudo-orbit. Okay, so I'm simultaneously moving all of these points, which is in this higher space is just one point, down to a manifold. That manifold is where the cost function is 0. All these guys add to 0, and that corresponds to a trajectory. So in the perfect model, I may want to go to a trajectory. I'll do the actual. I knew I wasn't going to get to it today, so I'll do it tomorrow. But that's probably where I should stop. The idea is just this: that by using this entire window, right? By using the information over the window, by using the dynamics in the model, without assuming it's perfect, right? We can actually get a much better result. Well, why isn't this just variational assimilation? Well, the difference between variational assimilation is we start on the observations. So we actually start here, right? Variational assimilation has to respect a term which includes a distance between the trajectory, the variational trajectory, and all these points. So that's what creates all the local minimum. Our method, we basically start on the observations and then we let go of the observations completely. And the result of that means that our initial condition, the blue dots, which you probably can't see, are all close to the truth if it exists. And we're not constrained by these local minima don't exist. We can move straight towards the better point simultaneously. But I'll do the math of this at the beginning tomorrow. Okay? And that I'm really happy for questions. If you have any. Sorry, the last part?
The one you were talking about,
Uh-huh.
kind of doing it with the window over a period of time. How is it different from 4D bar?
Okay, so it's different from 4D bar because the 4D bar cost function has 2 terms in it. Right? Well, actually, the 4D bar, you're making variations in x0, right? You're making variations of the initial condition only. And your cost function is a function of the distance between f of x0 and s sub I. So it's the difference between this observation and the trajectory, this observation and the trajectory, this observation and the trajectory. So this is a very poorly behaved cost function in that it has loads of local minima. You're trying to be close to the. If you start with an initial x0 very, very close to the true value, everything is perfect. But if you start with a macroscopic error, then eventually this trajectory isn't close, and you get caught in these local minima. So why do we not get caught in these local minima? We actually start with x0, x1, x2, x3. So we actually go up to the suspension space. And all we're trying to minimize is f of xi minus xi plus 1. Right. So what we're doing is we're starting with a pseudo-orbit, again, I'll say this tomorrow very slowly, or whenever my next lecture is. We're starting with a pseudo-orbit. This is not a trajectory, which allows us to start very close or closer to the observations, and we're not trying to stay close to the observations. After the first iteration of this method, what we're trying to do is to find a trajectory close to this initial condition. It's only the initial condition that's defined by the observations.
So the observational error is irrelevant.
So the observational error has to do with the convergence, right? It may limit the convergence, but that's right. The observational error is not.
It's not factored into your method.
That's right. We have no metric. We don't specify a narrow covariance matrix, and what's more important, we don't specify a model error a priori.
So you believe the observation, so initialize the model from the first observation run until the next observation is available, switch over, start the model.
Exactly.
You do that.
Right. I wouldn't say we believe them. I wouldn't say we believe the observations, but we use them in exactly that way.
Then you are trying to squash those differences by doing a minimization. That minimization process, your model should come as a constraint.
That minimization.
You are trying to do some least square fit.
I know.
All the free variables are.
I'm trying to find that gives me a pseudo orbit.
Yes.
I'm trying to find a trajectory of the model near that pseudo orbit.
But then for that pseudo orbit, the model provides a constraint either as a weak constraint or a strong
Correct.
constraint.
Absolutely.
That's where the question of the relation to 40 var came about.
That's where the difference comes about. Because with 40 var, you basically you have with the strongly constrained 40 var, you have a trajectory from the very beginning, right? Which means that in fact, by the final time, if your window is long, it will systematically be far away at the end time. Whereas we start with a pseudo orbit, which is always near the observations, and we ask the question: is there a trajectory close by or not? So if the observational noise is too large, we'll fail.
Basically, weak constraint 40 var with infinite observation.
With
Infinite, R going to infinity.
now, so weakly constrained 40 var, you still have to specify a Q matrix for the model error. You still have to make assumptions about the model error, which we do not have to make. And you still have a term which is trying to keep you close to the observations, which we actually tried at first but threw away because it works better. It works just as well without it. Sorry, no. In fact, our assimilation can be very large. Like, so we've looked at no gaps. I'll show results tomorrow. The Navy's operational weather model with an assimilation window of about 7 days. With the T21 quasi-geostrophic model, we get improved results if we look even out to over a week, well over a week, 10 days or so. The reason we get better results is that there's a lot of information in the model, and we get information from the entire window. But if the model isn't perfect, then we have to have a weakly constrained form, as you suggest.
But the weakness is that your dimension of your observation space, from what you've said so far, has to be the same as the dimension of your physical state space.
So no, there's a requirement in both 40 var and our method and the common filter that we map the observations into the state space somehow. Right? So that's a shared constraint. I wouldn't call it a weakness. In fact, I think for our method, the quality of that initial guess can be a lot worse because we're pulling a lot more information out of the dynamics. So I think we just used optimal interpolation or a 3D bar. Basically, when we've done it with large models, we use some cheap method that they have nearby.
Well, that isn't quite. I mean, in 4D bar and common filter, you take an operator from the state space to the observation space.
Well, we can use the same Well, to run the model, no. You need both. In both cases, in both cases, you need both. You can't run the model unless you've mapped things into the state space. So to run the model forward, data assimilation
Created some analysis.
Right. That's all. That's the map I need. Data. That's my. Yeah. So you.
But then that means you have to go back to using a data assimilation method to create the operator that gets you into the state space.
That's correct. We need some cheap. We need some cheap way of quickly moving into the state space. That's absolutely correct.
do the students have any questions on this? I mean, we're asking Lenny to explain things that he's going to explain tomorrow morning, essentially. I think so. We're anticipating tomorrow morning's lecture. Is there any? The students have any questions on today's lecture? Yeah.
How you are relating the diagonal time?
Sorry, I can't quite hear you. Okay. So,
I think it's all
I mentioned these things called Lyapunov exponents, and there's something called the Lyapunov time, which is 1 over the Lyapunov exponent. Let me define it, then I can ask you what you wanted me to relate it to, okay? So the easiest way to think about this is if you have a very simple map, f of x against x, right? 0, 1, 0, 1. So this is basically 2x mod 1. Okay, so I'm basically doubling x on every case and then mapping it back into 0, 1. So I need to do this. Again, I hope this is a geometric picture. I hope it'll make sense. But any error I have is going to double on every step, right? X plus epsilon is going to go to 2x plus 2 epsilon, and my error is going to increase by a factor of 2. That's easy. That way I can actually show that my lambda is equal to 1 bit per iteration. Every time I iterate, it doubles. And, you know, for this map, which looks really nice and easy, the Lyapunov exponent completely determines the predictability. But this map is linear at macroscopic scales, for one thing. And the second thing, I can draw a map, an alternative map, which I can't write down the equation for, but looks something like this. This is sort of f of x is equal to alpha x, where alpha is 1 plus epsilon, and then put something very steep down here at the end. That 1 will do. This map make sense? So this map is uniform. This map is slowly increasing for almost all the domain, and then very rapidly increasing just down at the end. So this is x goes to beta times x, where beta is much, much greater than 1. This map has the same Lyapunov exponent. And I can work with alpha and beta so that, on average, the exponential growth is the same in each of those maps. But the predictability of those two maps is completely different. Because if I have an initial condition in the blue map down here, it's very easy to predict it. Persistence is a good predictor. It's only when it happens to be in this region down here that I have a problem. And if you go back, I can show this tomorrow too, if you like. If you look at most chaotic systems, except for the very simple ones created 100 years ago, right? But those were created, those are usually piecewise linear. They have some very, very simple structure. And that means that the Lyapunov exponents, or the local growth rate, is the same everywhere. Even if you look at things like Lorentz 63, the 1963 Lorentz model has a region in which all perturbations shrink. Right? You could actually see that on the little graph, right?
I want to see that slide. I have a question on that slide. Yes. So y-axis is Lyapunov time.
So y-axis is just time, right?
So when you are getting this bifurcation at 1.5.
So the y-axis is time,
Yeah.
right? The x-axis is x. So at time equals 0, I have some initial condition, some PDF from my assimilation scheme. at time equals 1, I'd move this forward. I have some new probability distribution. Does that make sense?
Yes.
No. As I move further into the future, my forecast probability for x spreads out. Okay? No, not okay. Okay.
Okay, I will.
Let's try again. So what?
We should do this as a private discussion over coffee.
And
The other one thing I should say is this picture is
This is a
in
good discussion, but maybe you and Jim Ralph.
this book, right? And I have a couple copies that I'll leave wherever, I'll give to him, and you can have it first. But so if you're more interested in chaos, then tell me. I can talk more about chaos. But you could also look at this book and then ask me questions about the book too.
Okay, so should we start again? What about, should we start at 20? Ahmed?
Yes, so
Should we start again at 11:20?
we
should also announce that today and tomorrow's tutorial are being switched. So actually today's tutorial will be nudging Didier, and tomorrow's tutorial will be MR based on this stuff. Okay, so we'll come back.